next we're going to look at the important idea of an isometry. So an isometry is an operator that has the property that it does not change the length of any vector. So if we take the input vector v and we look at its norm, and we take the output vector sv and we look at its norm, they're the same. Okay, so so sometimes people say S or an isometry preserves norms. What comes out is the same as what went in. So S doesn't change lengths, just directions. And so you might wonder, is it possible to have an operator that preserves the length of all vectors, but somehow changes the angle between them? And then by thinking about triangles, you realize, oh no, the answer is no. It has to preserve angles as well, because otherwise hypotenuses would get stretched and that kind of thing, right? So it actually, there's in the next clip we'll see a characterization of all these kind of properties. The reason why the definition is presented in terms just of lengths is because this makes it work more generally. So it works in a norm to space that does not have an inner product, for example. Okay, so we will also see that an isometry maps an orthonormal basis to an orthonormal basis. And this is how you should think of an isometry. So if our vector space is C to the n, then it is a composition of reflection and rotation. So sometimes this is called a rigid type transformation because the distances don't change. So in particular, there's no scaling, there's no shearing, there's no projection. Those are all things that change the length of vectors. And so you should imagine, like, if I have some little orthonormal basis like this, and then I pick some other little orthonormal basis like this, pretend those are all mutually orthogonal vectors, then basically S is going to be a mapping from one to the other that pairs up those orthonormal basis vectors. And conversely, if it pairs up orthonormal basis vectors, then it's going to be an isometry. And so here's a little example just to sort of riff on that idea. If we take an operator and if V has an eigen, oh shoot, that was just a mess. An eigenbasis, or actually, yeah, no, it's gonna mess up my grammar. Sorry. Has a basis of eigenvectors of S whose corresponding eigenvalues all have magnitude 1, then S is an isometry. Okay. So and then later on we'll see. So this is the forward direction, this then right here, And later on we'll see that the backward direction also holds if we're in the complex case. So for right now, however, let's just see. So if we have v and v, we can take v and write it in terms of the eigencoordinates. So orthogonal decomposition with respect to the eigenbasis. And then you can see that SV is going to be the sum of VEK SEK. And when we apply S to that, it's going to kick out a lambda. So it's this old story again, right? Okay, so now taking norms, the magnitude squared of V is going to be, by the orthogonality of the eigenbasis, the sum of the components squared in modulus. And then taking norms of the other equality as well, the norm squared of the SV part is going to be, and then we have, again by Pythagoras, since these guys are all orthogonal, the magnitude squared of these ones. Now we can use the rule for absolute value, and then we're assuming that all of these guys are equal to 1, and so that shows us that this is actually equal to magnitude squared of V. Alright, so taking square roots of both sides, we see that we've got an isometry.